thanks for this opportunity to give this tutorial about uncertainty quantification deep neural networks. As already introduced, my name is Fabian Brickwedde. I'm an employee at Robot Bosch company and also a PhD student at the Goethe University of Frankfurt. My PhD supervisor is Rudolf Meester, and my major topic is about computer vision. So you will also see during the tutorial that many applications are motivated by computer vision. This tutorial is separated into 4 parts. So the first part will give a short introduction and motivation. So basically, why do we need uncertainty quantification for deep neural networks? The second part explains the different types and sources of uncertainties and gives also an overview of how to quantify those different types of uncertainties. The third part is about calibration. So in a classification problem, you often use a softmax layer and therefore you get a score between 0 and 1. So one may ask, what is wrong with these network scores? Why do we need all these uncertainty quantification stuff? And this question will be addressed in the third part, especially in terms of having a look of the calibration of neural networks, which will answer then the question why we cannot just use the network scores. The fourth and final part will then give a more practical view on uncertainty quantification. So I will show you an application which was developed in my group, which is about probabilistic single view depth estimation. So it will also answer you some question how to develop a probabilistic neural network, how can you evaluate it, and all these stuff. So let's start with the introduction and motivation. So why do we need uncertainty quantification? Therefore, I want to start with a small application, which is shown in the figure. And this application is about automated diagnosis of diabetic eye disease. So in this application, based on an image of the eye, the network classifies this eye as being healthy or unhealthy. However, the problem is without an uncertainty measure, each wrong classification would directly result in a wrong diagnosis. And therefore, shown in the left picture, there's an application proposed based on a probabilistic model. So you want a probabilistic model that predicts you additionally an uncertainty. And if the uncertainty of the classification is too high, then the diagnosis is handed over to a human doctor. And only if the network is sure about its classification, it is used as a final diagnosis. So this application highlights also the first field of applications, which are safety critical applications. Other examples for safety critical applications are, for example, autonomous driving or different medical applications. As a second type of applications, I want to mention the sensor fusion and tracking. For sensor fusion and tracking, you want to know which estimates you can trust more for a proper fusion. So if you want to combine 2 estimates, you basically need to define the weighting of both estimates, and therefore you need the uncertainty of them. The third field of applications are the active learning. So in active learning, you are interested in a smart selection of training data. The reason is that the labeling process of training data is quite expensive, and therefore you want to choose these data samples where the network will benefit from. So therefore you look at the uncertainty and will start to label these data where the network is uncertain and hope that these samples will then help the network to get better and not to label too much data that is not needed for further training. And these are just 3 applications that came into my mind. So there will be much more applications that benefit from uncertainty quantification. So the second topic is now about the types of uncertainty. What are the sources of uncertainties? So where does they come from? And therefore I want to start with a toy example, which should demonstrate the different types of uncertainties. So in this toy example, you see a function which is something like a sinus, and the network is trained to predict the y value based on the x value. So predict the vertical axis based on the horizontal axis as input. Additionally, the input data is added with some Gaussian noise, so you don't have perfect ideal data. And for training, you use the blue data samples. The orange areas or the orange data points were never seen by the network. The result of some networks are shown as black or red curves. So now I want to show you the different kinds of uncertainties. The first kind of uncertainty corresponds to the added Gaussian noise and is called the measurement or aleatoric uncertainty. So due to the Gaussian noise, an X value is no longer uniquely assigned to one Y value, and this introduces some ambiguity or uncertainty to predict the Y value based on the X value. In other examples, this ambiguity is also from a more systematic nature of the problem. So for example, in computer vision, if you take an image of the real world or take an image of a miniature world, but with a camera close to the miniature world, the image could in the ideal case look identically the same. And so therefore you have the same image, but the characteristics of the scenes are different. So in a miniature world, for example, the distance to the camera and the size of the scene is much smaller. One good point of the measurement uncertainty is you can see this uncertainty during training, because also during training your input data is typically corrupted by the Gaussian noise. So the second kind of uncertainty is now the model uncertainty or epistemic uncertainty. So if you train a model, you will typically get one solution for the model weights. But on the other hand, if you train the model multiple times, you will also get different model weights. So, and this highlights the case that there are many parameters that could describe the training data at least similarly well. And this then highlights that there's some uncertainty of the model parameters and not just one set of parameters that is perfect for the training data. And exactly this case is addressed by the model uncertainty. And you see in this figure the different networks and their results. So for the blue area, all networks provide nearly the same output, but you see also for the orange part that the different networks provide much more diverse estimates and therefore a higher uncertainty in these areas. And exactly this case is also sometimes made explicitly. So the fact that the networks provide higher uncertainties if the test data is different from the training data. And this is then called out-of-distribution detection or distributional uncertainty. And as mentioned, this relates to the mismatch of the training and test data. So in the following slides, I want to give an overview of methods, how to quantify the different types of uncertainty. So as you can see in the figure, in a normal deterministic neural network, you get one deterministic input and estimate merely the maximum likelihood estimate. So especially if you think about a regression problem, you will just get one output value. The first strategy now for quantifying the measurement uncertainty is to replace this maximum likelihood estimate with an output distribution, as you can see in the right figure. So for example, assuming a Gaussian distribution, the network would now estimate the mean value and a variance instead of just one maximum likelihood estimate. This output distribution can be trained by minimizing the negative log likelihood as a loss. And so if you look at the equation, you see that the error is weighted inversely by the variance. So this means an error has a lower impact on the loss if the variance is high, and therefore the network starts to predict high variances if it assumes that the corresponding estimate has a high error. However, you can also see, due to the second part, that the network cannot simply estimate high variances for all estimates. So the network must balance which errors are expected to be low and they get a low variance, and which estimates will have a high error and therefore get a high variance. Okay, so this is the first approach to estimate the measurement uncertainty. And I also want to highlight a second kind of approach. And the second approach is to quantify the measurement uncertainty by making the input noise more explicitly. So if you look at the right figure, you see that it is assumed that the input has a certain uncertainty, and which is defined by some input variance. And this input variance is then propagated through the network, so which means that all activations of the hidden layers are now distributions. So all activations provide a mean and a variance, and not only one value as in a deterministic network. So this propagation also does not require any special training. It's really just traditional statistic way of propagating uncertainties through the network. Okay, so now I want to show you some examples. So the figure shows some results for an approach for semantic segmentation in street scenes. And you can see that the measurement uncertainty in the right column. You see that the measurement uncertainty is typically high at the boundaries of objects because there it's hard to distinguish to which object the pixel belong. And you also see that the variances are typically high at far distances, so where the object size in the image gets very small. Okay, so now this were two approaches for quantifying the measurement uncertainty, and now I want to show something regarding the model uncertainty. So approaches for the second kind of uncertainty, the model uncertainty, are now presented here, and the model uncertainty was motivated by the fact that there might be many combinations of model parameters that explain the training data similarly well. So therefore, in Bayesian deep learning, the model and its parameters are replaced by distributions, as you can see in the right figure. And so the data set is now used to model the distribution of the model parameters, which is highlighted by the red lines. So basically a probability is assigned to each possible model so that models that fit well to the data set get a high probability. After that, so to derive the distribution of your estimate, you can now integrate over all possible models and weight the estimate of each model based on its probability. And additionally, you typically assume have some prior assumptions. So for example, that each weight can be described as a Gaussian distribution. However, there's one problem with Bayesian deep learning. So especially for huge networks, this computation is basically infeasible or at least very expensive. And so therefore, many approaches try to approximate this Bayesian inference. And one popular approximation is using dropout during inference, as you can see in the right figure. So dropout was also presented in the first talk, and dropout removes the node from the graph with a certain probability. Traditionally, dropout is just used during training, but in this application, they also use dropout during inference. So this, if you run the network multiple times, this dropout during inference, this corresponds to a very simple assumed distribution that each weight is either 0 or gets its normal weight. And therefore you sample estimates from the network, and the distribution of these network or these samples then encapsulates the model distribution. So therefore I want to show some example results for the model uncertainty, which is shown in the right column. And you see, in contrast to the measurement uncertainty, the model uncertainty does not provide high uncertainties for object boundaries or at far distances. It captures more the uncertainty for untypical areas. So, for example, unusual textures of the road or sidewalk. So the third kind of uncertainty is now the out-of-distribution detection. So it refers to the fact that the networks typically provide erroneous estimates if the test data is too different from the training data. And the first idea to detect these samples is relatively straightforward. So the problem of the out-of-distribution data is that such data is simply not given during the training. And therefore, there are some approaches that try to generate samples that represent the out-of-distribution data. So if we would have such out-of-distribution samples during training, the network can then be trained to provide a high uncertainty for these samples or to directly detect the out-of-distribution samples. And yeah, this figure shows now a method that uses a generative adversarial network to generate samples at the boundary of the training data as shown in the left figure. And yeah, the right figure shows the same approach for applied to the MNIST dataset. So MNIST is a dataset with numbers, and you see that the generated samples look like digits, but they are no real numbers. So they are really at the boundary between being a real number or something else. So the second kind of approach, which still addresses the detection of out-of-distribution samples, is to analyze the activation in the latent space or the hidden layers. So typically we look at the final results after the softmax layer and interpret these scores as the classification. However, also the hidden layers provide information which class is the most likely one. So for example, some activations are activated if subparts such as a head is detected. And yeah, therefore, each class has a typical pattern of activations in the hidden layers, and this can also be modeled as distributions. And now, yeah, in contrast to a data sample close to the training data, an out-of-distribution sample or also an adversarial data sample shows a very untypical pattern of activation. This is shown in this figure for an adversarial example of a panda. And so, yeah, as you see in this example that even though the final classification of the adversarial attack is a school bus, if you look at the hidden layers, it looks like a mix of a school bus and a panda, as you can see in the right figure. Okay, so now the next part is about the calibration of neural network. So as already mentioned at the beginning, in a classification problem, the network provides a score for each class, and also all scores sum up to 1. So these scores actually fulfill the requirements for discrete distribution. And now in this part, we want to have a deeper look into these network scores and why do we need all these uncertainty quantification stuff. So first, as classification models are often trained by minimizing a cross-entropy loss, the network scores capture the measurement uncertainty. So they refer to the first kind of the presented uncertainties. And now the calibration is, for the calibration, we look if the confidences correspond to the accuracy. So considering the example shown in the figure, the network provides scores that the eye is healthy, for example, with a confidence of 80%. And now for a well-calibrated model, we assume that a score of 80% is equal to a probability or accuracy of 80%. And now to rate the calibration of a model, this can be done in the following way. So we take all estimates with a score of 80% as shown in the blue box, and now analyze the accuracy on a test set as shown in the green box. And yeah, for a well-calibrated model, we assume that the accuracy for all confidence, so for a confidence of 80%, we assume that the accuracy is also 80%, so that 4 or 5 estimates are correct. And this analysis was now done in a paper which compares the confidence to the accuracy. So this analysis is done for 2 networks. One is an older and smaller network, the LeNet, and one is a more modern network, the ResNet. So the histogram shows now the relation between the confidence predicted by the network and the real corresponding accuracy. The confidence or the network scores are shown on the horizontal axis and grouped into bins of 10%. And the corresponding accuracy is shown on the vertical axis. And now you can look at the figures. And so, for example, the network scores between 80 and 90% of the ResNet correspond to an accuracy of around 40%. So this shows that the network scores predicted by the ResNet suggest a much higher accuracy than it actually is. And yeah, for a perfect calibrated model, we would assume that all bars lie on the diagonal. And what is interesting is that for the older network, the DNet, this is nearly the case. However, the overall error of the ResNet is much better. So it is not really attractive just to use the DNet because it is better calibrated. Yeah, and so this work also analyzes what is the reason for the modern networks that they are worse calibrated. And here they analyze different architectural choices and training strategies and their impact on the calibration error. The calibration error here is denoted with the expected calibration error, ECE. And you see that for these 4 different architectures and training strategies, there's often a conflict between the error and the calibration. So the modern networks that get better in terms of the error due to higher depths or more filters per layer, this on the other hand results then in a worse calibration, which is one reason why especially the modern networks are bad calibrated. So, but now it's not really an option that we just use the worst network to get a better calibrated one. And therefore there are other approaches proposed that are called recalibration and now try to compensate the effect of the miscalibration of the networks. So therefore the uncalibrated confidences of the networks are mapped to new calibrated confidences. And yeah, so similar to the evaluation shown in the previous slides, this relation is determined on some holdout split, so which is not used for training. And then based on this analysis, a function is determined that maps the uncalibrated confidences to new calibrated ones. And you can see this here for 3 different methods. The methods basically differ in how they formulate the mapping. However, the diagram shows that all provide a much better calibration than without these techniques. Okay, so now the final part will be give more practical view on uncertainty quantification, and I will show you some method in the context of probabilistic single view depth estimation. Yeah, therefore I want to start with single view depth estimation. So single view depth estimation is a computer vision analysis of the pixels to the camera for video input. And yeah, these are the results from one of the currently leading approaches. Okay, so the method I have shown is just provides a single depth estimate for each pixel. And now I want to show you something regarding probabilistic single view depth estimation. And this is a method developed in our group, and we called it ProbDepthNet due to this probabilistic characteristic. So ProbDepthNet basically addresses the measurement uncertainty, so the first kind of uncertainties I introduced in the beginning. And yeah, so therefore the output of the network is not just one maximum likelihood estimate. Instead, it are the parameters of a distribution. And here we choose a mixture of Gaussian. So for each pixel, you get some mean values, variances, and weights to describe the distribution. The architecture of the DepthNet is nothing special. It's simply a ResNet 50 with skipped connections. And this network uses a supervised training and is trained on some ground truth data from a LiDAR sensor. The ground truth is additionally computed using completed using a stereo sensor. Yeah, so to be honest, it's not so important. The main reason for this is to overcome some limitations of the LiDAR sensor, which, for example, only provides depth estimates up to 80 meters. The training loss is the same as proposed in the beginning, so we minimize the negative log likelihood. And yeah, therefore these distributions also correspond to the measurement uncertainty. So these figures show now some qualitative results of the DevNet part of the prop DevNet, and the third column shows the mean value or the maximum likelihood estimates, and the fourth column shows now the corresponding variances. And you see that the variances or uncertainties are typically high at object boundaries, so where we have some depth discontinuities. On the other hand, there are also some parts with quite low variances, for example, the street. The reason that the street has such a low variance is basically that the street follows a very strict model assumption. So especially if you assume a flat world and your data set does not have too much sloped streams inside it. Also interesting is the last example, which is a dark tunnel. In this example, you see that the depth estimates are more or less completely wrong. However, also the variance is quite high for almost the whole image in this scenario. So these figures showed some qualitative results, and now we want to have a look at the quantitative evaluation of these uncertainties. And therefore I want to present the first kind of plots, which is a sparsification plot. In a sparsification plot, on the horizontal axis are the fraction of removed pixels. So you order your estimates by their uncertainty and now remove gradually the pixels with the highest uncertainty. And on the vertical axis, then you evaluate the root mean squared error. So the reason is, if you look at this curve, you see that it is monetarily decreasing. So if you remove the points with the highest uncertainty from the left to the right, your error decreases, which shows that the uncertainty corresponds, so that high uncertainties corresponds to high errors. And yeah, so this was more a visual impression how that the curve is decreasing, and you can also determine some metric to rate the quality of the uncertainties. So therefore, there's one additional curve shown, which is called oracle. The oracle always removes the point with the highest uncertainty. So this is basically the best curve you can get. And if you now determine the area between your curve of the estimated uncertainties to the curve of the oracle, this can be used as a score, and this is called area under sparsification error. So the sparsification error does not say anything about the calibration. It just says that higher uncertainties correspond to higher errors, and therefore you can also evaluate the calibration using some calibration plot. In a calibration plot on the horizontal axis, you have the confidence interval, and on the vertical axis, the frequencies of ground truth values lying in such confidence interval. So for this example point, you take the confidence interval of 60% of all estimates and look how many ground truth values lie inside this interval. And in this, for this example, it would be that 20% of the ground truth values lie inside the 60% confidence interval. For a perfect calibration, the confidence interval and the frequency should be the same. If this is not a case, every point that lies right from this line shows overconfidence distributions, and everything on the left shows underconfidence distributions. And this is now shown for the DevNet here, and you see that the DevNet is quite overconfident. So this is nearly the same as shown for the calibration of the classification problem. So the same issue also appears in a regression problem shown here for the single view depth estimation. And if you now want to get the final metric, you can again compute the area between the perfect calibration and your results, which is then known as expected calibration error. I also want to briefly show how to integrate a recalibration method in this kind of approaches, which we call Calipnet. So the Calipnet are some subsequent layers that take the uncalibrated variances and weights as inputs and maps them to new calibrated ones. The Calipnet layers are trained just using an NLDL loss, so the same as for the DevNet. And the trick that this calibrates the variances and weights is that these Calipnet layers are trained on a different split, which was never seen by the DevNet. So the DevNet cannot overfit on the calibration split, and therefore the distributions estimated on this holdout split are much more representative for the data in general. Yeah, the Calipnet is basically one residual block, so even if it looks like an additional network, it's just a few layers and does not introduce too much overhead. Yeah, so finally, I want to show you visually what's happened, including this recalibration technique. You basically see that the variances get much higher, and this is also plausible because this DevNet was shown to be overconfident, so increasing the variances is plausible. If you look at the plot, the sparsification plot basically does not change because the sparsification plot does not address the calibration. But if you look at the calibration plot, you see that the calibration, including this Calipnet, gets much better, and also the expected calibration error decreases by a factor of 7. So as my last slide, I want to come back to the different types of uncertainties. So the prop DevNet only addresses the measurement uncertainty. And here are some examples shown from a different data set. So these examples are from the Make3D data set, which captures a wide range of auto scenes. And the prop DevNet was only trained on typical street scenes. And you see in the the right figures that these close-up views of buildings that were never part of the training set result in quite bad depth estimates, but also in quite bad variances. And this motivates that the measurement uncertainty alone is not enough. So you additionally need the other also to address the other kind of uncertainties, such as the out-of-distribution detection, as in this example. Yeah, and with this, I want to close my presentation and thank you very much for the attention.